presentation. My name is B. Nandakishore. My number is 21951804A9 and I am from ECB section and my subject is SS. My topic is applications of Z transform. Introduction. In mathematics and signals processing, the Z transform converts a discrete time signal, which is also sequence of real or complex number, into a complex frequency domain, Z domain or Z plane representation. It can be considered as a discrete time equivalent of the Laplace transform S domain, whereas the continuous time Fourier transform is evaluated on the Laplace S domain's imaginary line. The discrete time Fourier transform is evaluated over the unit circle of the S domain Z domain. What is roughly the S domain's left half plane is now the inside of the complex unit circle. What is the Z domain's outside of the unit circle roughly corresponds to the right half plane of the S domain, where the continuous time Fourier transform is evaluated on the Laplace S domain's imaginary line. The discrete time Fourier transform is evaluated over the unit circle of the Z domain. What is roughly the S domain's left half plane is now the inside of the complex unit circle. What is the Z domain's overside of the unit circle roughly corresponds to the right half plane of the S domains. One of the means of designing digital filters is to take an analog design, subject them to a bilinear transform which maps them from the S domains to the Z domains, and that produce the digital filter by inspections, manipulations, or numerical approximations. Such methods tend not to be accurate, except in the vicinity of the complex unity, i.e., at low frequencies. One of the means of designing digital filters is to take analog designs, subject them to a bilinear transform which maps them from the S domains to the Z domains, and then produce the design filter by inspections, manipulations, or numerical approximations. Such methods tend not to be accurate, except in the vicinity of the complex unity. At low frequencies, definition: the Z transform the Z transform can be defined as either a one-sided or two-sided transform, just like we have the one-sided Laplace transform and the two-sided Laplace transform. Definitions: the Z transform can be defined as either a one-sided or two-sided transform, just like we have the one-sided Laplace transform and the two-sided Laplace transform. The Z transform can be defined as either one-sided or two-sided transform, just like we have the one-sided Laplace transform and the two-sided Laplace transform. And bilateral Z transforms. The bilateral or two-sided Z transform of a discrete time signal x of n is the formal power series x into s, defined as x into s, x of z equals to z of x of n equals to sigma infinity n equals to minus infinity x of n z to the power minus n, equation 1, where n is an integral and z is in general a complex number. Z equals to a j naught equals to a naught into cos naught plus j sin naught, where a is the magnitude of z, j is the imaginary unit, and theta is the complex argument, uh, also referred to as angular phase in radians. Unilateral Z transform. Alternatively, in cases where x of n is defined only for mm, n less than 0, the single-sided or unilateral Z transform is defined as x of z equals to z of x of n equals to sigma infinity n equals to 0 x of n z minus n equation to. In signal processing, the definition can be used to evaluate the transform of the unit impulse response of a discrete time causal system. Inverse Z transform. Uh, the inverse Z transform is x of n equals to z to the power minus n, x of z equals to 1 by 2 pi j psi of c x of z into z to the power of n minus 1 dz, where c is a counterclockwise closed path encircling the original and entirely in the region of convergence or rock. In the case where the ROC is causal C, example, the means the path C must encircle the of the poles of x of z. In special cases of the counter integral occurs when C is the unit circle. The counter can be used when the rock includes the unit circle, which is always granted when x of z is stable. That is when all the poles are inside the unit circle. With these counters, the inverse Z transform uh, simplifies to the inverse discrete time Fourier transform of Fourier series of the periodic values of Z transform around the unit circle. X of n equals to 1 by 2 pi psi plus pi minus pi x of j x of e j omega into e j omega and d omega. Region of convergence. The region of convergence ROC is a set of points in the complex plane of which is the transform simulation. Convergence ROC z sigma infinity n equals to minus infinity x of n z minus 1 greater than infinity. Number of ROC, let x of n equals to 0.5 n, expanding uh, x of n on the interval into minus infinity infinity, it becomes x of n equals to bracket dot 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 comma 0.5 to the power of minus 3, 0.5 to the power of 2, 0.5 to the power of minus 1, 1 0.5 0.5 to the power of 2 and 0.5 to the power of 3 bracket close. Looking at the sum, in sigma infinity n equals to minus infinity x of n z minus 1 to the infinity. Therefore, there are no values of z that satisfies this condition. Relationship the two Laplace transform. The bilinear transform can be used to convert continuous time filters represented in the Laplace domain into discrete time filters represented in the Z domain, and vice versa. The following substitution is used: is equals to 2 into z minus 1 by t z plus 1 into the to convert some functions of s in the Laplace domain to a function h of z in the z domain test and transformation, or z equals to e s st equals to 1 plus s t by 2 by 1 minus s t by 2 for the z domain to the Laplace domain through the bilinear transformation. The complex s-plane of the Laplace transform is mapped to the complex z-plane of the z transform. While this mapping is necessarily nonlinear, it is useful in that it maps that the entire display style j by omega bracket close axis of the s plane into onto the unit circle in the z plane. As such, the Fourier transform, which is the Laplace transform evaluated on the display style j omega axis, becomes a discrete time Fourier transform. This assumes that the Fourier transform exists, therefore that the display style j omega and display style j omega axis is in the region of convergence of Laplace transform. Bilinear transform. The bilinear transform can be used to convert uh, continuous time filters represented in the Laplace domain into discrete time filters represented in the Z domain, and vice versa. The following substitution is used: Z equals to 2 by t by into 2 into z minus 1 and by t into z plus 1 to convert some to convert some functions h of s in the Laplace domain to a function h of z in the domain h of z in the domain Dustin transformation, or z equals to e s of t equals to 1 plus st by 2 by 1 minus st by 2. Started transform. Give a one-sided z transform x of z of a time sample function. The corresponding started transform produces a Laplace transform and restores the dependence on sampling parameter t is to x into of s equals to x of s z equals to e s of t. The inverse Laplace transform is a mathematical abstraction known as an implements of sample functions. Linear constructions, coefficients, differentials, equations. The linear constant coefficients differences LCCD uh, equation is a representation for a linear system based on the autoregressive moving average equations. Sigma n p equals to 0 y into n minus p into alpha p equals to sigma m q equals to 0 x of n minus q on into beta q. Both sides of the above equations can be divided by alpha 0. It is not 0. Normalizing alpha 0 equals to 1, and the LCCD equation can be written y n equals to sigma m q equals to 0 x of n minus q b q minus sigma n p equals to 1 y into n minus p into sigma p alpha p. Output response. If such a system h of z is driven by a signal x of z, then the output is y of z equals to h of z x of z. By performing partial fraction decomposition on y of z and then taking the inverse z transform, the output y of n can be found. In practice, it is often useful to fractionally decompose y of z by z before multiplying that quantity by z to generate a form of y of z which has terms with easily computable inverse z transform. And conclusion: the z transform proves a useful more general from a discrete time Fourier transform series. It applies equally well to describing systems as well as signals using the eigenfunctions method, and proves extremely uses in digital filters. Conclusion: the Z transform proves a useful more general form of the discrete time Fourier transform. It applies equally well to describing system as well as signals using the eigenfunctions methods, and proves extremely useful in digital filter design. And this is the conclusion. And thank you.